This looks a little bit different than my classroom at Duke. It's a lot taller. You guys are way up there. You guys are getting a hell of a deal today. Duke normally charges $90,000 to hear me talk about AI, and you guys are getting this for $99 or something like that. Great. So I'm going to talk today about search and how it's evolving in the age of AI. Quick introduction, as Mark mentioned, I'm the faculty director of our AI Masters of Engineering program over at Duke University, right here in town. For anybody who's thinking about going back to school, we have an online program. We have a part-time in-person program. We'd love to talk to you about that if interested. And we've got a booth right up there you can stop by. As Mark also mentioned, I'm also an entrepreneur, so I run a Duke spin-out that I co-founded with my co-founders here, Pramod Singh, that's called Inquisite, and we are working to accelerate scientific discovery by building agentic AI that supports the workflows of researchers and science teams. And so I'm going to weave a little bit of that into my talk today because I thought it'd be more interesting for you to hear about things in real life that we're doing rather than sort of theoretical things that we tend to teach in the classroom. Okay. So we're going to start with just a real quick refresher on some Why is everybody laughing? Of course I'm kidding. There's no math involved. Don't get scared. I was hoping to see some people actually stand up and walk out. I didn't say they walk out. I guess you figured that out pretty quickly. No math involved in this talk. This will be a little different than my normal classroom lecture session. Some of my students in the room here can vouch for that. We're going to start with some of the basics. So for 25 years, this is what search looked like to us, right? It was Google mostly, maybe a few others. It was scrolling through sort of long lists of blue links, trying to figure out which one might be the right one to click on. Clicking on it, maybe you got it on the first try, maybe you didn't, then you go back and you try another one, and you keep going back and forth. Locally on your laptop, it was kind of a similar experience, but actually even worse, because now rather than having at least a little snippet to go off of, you basically just have the title of your file. So if I wanted to see where in my lecture slides I was talking about gradient descent, I don't know if it's week 4, week 7, week 8, another week 7. I have no idea until I open these files and go and look and figure it out, right? The world has changed, so the new way of search looks more like this. And this is a screenshot from ChatGPT, but there's lots of similar offerings from Perplexity and several others. So we just ask a question. We can ask it in natural language. We don't have to kind of carefully craft a good query. We just ask whatever's on our mind, and we get a synthesized response that's using sources. And this is somewhat new, at least in ChatGPT, Perplexity, and some others have been around for longer. Used to be that we'd put in a query like this, and we'd just get a response, from the large language model based on the data that it was trained on, without sort of reference back to any specific sources. Now, depending on what you ask it, as in a case like this, it may conduct an internet search to find relevant information to use to answer your question. And in this case, that's exactly what it did. I asked what Masters of Engineering programs are offered at Duke. It quickly determined it didn't know the answer to that question based on the data it was trained on, so it conducted an internet search, found a couple of relevant websites, and then formulated an answer to my question based on the information from the websites it's found. And it's provided some links back to the sources. So if I want to dive into any of these sources, I can just click on the link, and I can go and I can read it for myself. Okay, so very different experience. Better in some ways, maybe worse in a couple of ways, but certainly very different. This type of response is based on something called retrieval augmented generation, or RAG. I think you've heard a lot about RAG so far in the conference, so I'm not going to spend a lot of time covering it. But with retrieval augmented generation, we're trying to combine the parametric memory of a large language model, so the information that's compressed and stored into the weights or the parameters of that model, with a non-parametric source, which typically is a database that we're hooking the large language model up to. And it involves two steps. The first step is searching for information. So given some query, it goes and executes a search. It searches the database, it searches the web, uses maybe an API to do a search. It grabs all of the relevant information it finds, it puts it into a prompt to a large language model, and then in step two, it uses the large language model to generate a response back to your original question based on the information that it's found through its search in step one. Okay. This is a typical flow of what a RAG system looks like. Those of you that were at the training yesterday are probably very familiar with this approach. There's a lot of upfront work involved in building a RAG system, which is on the left side there, the data preparation step. So you take your entire sort of corpus of material, maybe it's your product specifications, maybe it's your all your PowerPoints on your laptop, all my lecture slides, maybe it's the entirety of the internet you've indexed, but whatever text data you have or multimodal data you have, you take it, you chunk it up, you break it up into small chunks of material, you create what we call an embedding of each of those chunks. And an embedding is a vector representation of the information within that chunk. So it's a set of numbers, anywhere from, let's say, 50 numbers up to a couple thousand numbers, and those numbers represent the semantic meaning of the information in that chunk. And we use an embedding model, which is a form of large language model, to create this vector representation. And we store all those in our database. And then when somebody comes to our website or our app or whatever and asks a question, the first thing we do is we take the user's question, we create an embedding out of that question, and then we compare the vector representing the question to the vectors of all the chunks stored in our database. We find the most similar vectors, we grab the information out of those chunks, we feed it to a large language model, and we ask the large language model to then generate a response back to that question based on the information from those chunks we've given it. And so this works great with files, PDFs, PowerPoint, Word docs, etc. But it also works with other forms of material, images, the internet as a whole as well. And this is the most common form of RAG, but it's not the only way that we can do RAG. There's actually a few different methods. And when we think about search, there's a lot of different algorithms that we can choose from. They sort of generally fall in one of two classes, either keyword-based methods or semantic-based methods. So keyword methods are sort of your more old school traditional search approach that works off of keyword matching, right? So it uses the words that you've put into your query, and it tries to find words in your corpus of material that are exact matches, usually. And we can do simple things like we count up how many matches there are within a document to the words in your query, and the more matches, the more relevant that document probably is to answer your question. We could be a little more sophisticated, and we can use things like term frequency. We know that some words occur in the English language much more frequently than others, so we can give heavier weight to sort of less frequently occurring words in doing that matching. So there's a whole variety of different algorithms we can use, but they all revolve around the idea of sort of keyword matches. The second sort of bucket of methods are the semantic methods, and these are what I just mentioned on the last slide. These are the ones commonly used with RAG systems, and these involve converting language into vectors, sets of numbers that represent the semantic meaning of the language, and then comparing numbers. And so we use a similarity metric to compare the vector representation of a query with the vector representation of all of the documents within our corpus. And we'll use a metric to find the most similar documents to our query, and we'll grab the information out of those documents and feed it to our large language model. There are pros and cons of each of these methods, actually. So the semantic methods, one of the big advantages there are it doesn't rely on exact matches for keywords. And two, it generally does a better job at being able to infer the context or the intent of the user's query. right? Keyword matches really don't make basically little to no attempt to infer what are you trying to ask. They're just using the words that you've used and trying to find matches. They're not actually trying to get at what did you actually mean? What do you actually mean when you're asking that question? What are you trying? What's your objective? What are you trying to get? And that's the kind of the big advantage of the semantic methods over the keyword methods. That being said, for certain types of searches, keyword methods can exceed the semantic methods. And so with our company, Inquisit, we actually use both of these, but we do use keyword methods because we find that for very niche topics, like the types of questions a scientist might ask, for example, often a keyword matching can outperform trying to do semantic matching. There's also a whole set of approaches that are kind of hybrid approaches that will use both of these in different ways. And you can actually do them in either order. So you can kind of start with keyword matching and you get a large set of possible matches, and then you use semantic matching to kind of rank those matches. Or you can do the reverse. You can use semantic matching to match on semantic meaning, and then you can use keywords to kind of filter out to a short list of matches. And so some of the best systems out there today for RAG are using both of these together. I wanted to talk a little bit about some sort of enhancements to RAG systems, because kind of the stereotypical RAG system, like I showed in that diagram on the other slide, often are somewhat naive and do a reasonable job, but not necessarily a great job at answering users' queries. And so I thought I'd talk about, kind of highlight three of what I think are kind of currently the most interesting opportunities for improvement on sort of the naive RAG method. The first is what I call query optimization. And so for us in Inquisit, we found that this has been a really important step for us. And one of the things we learned early on when we launched, so one of the tools that we provide researchers is what we call a research assistant. And so you can ask a sort of plain English question, and it will go and execute a search through the academic literature and go through and review papers and find relevant papers and evidence to support a conclusion on the question that you're asking. And one of the things we learned very quickly is that people in general, including scientists and researchers, are not very good at framing their questions. When we looked at the logs of the questions people were asking, it's like sometimes hard to even tell what they're trying to get because they're in a hurry, or they didn't sort of take the time to sort of think about how to properly frame the question, or they're misspelling things or using incorrect grammar and so on. So one of the things that we added very early on that I think has made a big difference is a query optimization step, where we'll look at what the user has put in that text box. And we'll try to take our best guess at what they're actually trying to get at, and we'll rewrite the query for them based on that before we go and execute a search. And then we'll search on the improved query rather than the original query. So I think that's an interesting area for improvement on kind of your standard RAG system. A second one is what I call routing. And so the idea here is that some queries you would want a RAG-based method where you'd want to go and search for sources. For other queries, you probably don't need to. And so one of the things that people are doing now is inserting sort of a model to look at your query and quickly make a determination. Can I answer this question just based on my training data alone, or do I need to go and execute a search to find information to answer this question? There are multiple benefits of that. Probably the largest one is reduction in cost and latency. So if you don't have to go and execute a RAG approach to answer a question, you're better off just answering it without doing the RAG, because you save money and you save time. You get a response back to the user more quickly. You can possibly also use a much smaller model versus a larger model, and you can further reduce latency and time. And then the third area I want to highlight here is what I call is using a large language model to do a review and or ranking of sources that are found through a RAG system. And there's a lot of fancy names for this, and different research studies have been published. But the general idea here is that when you do your RAG, you get a bunch of sources, right? And up until that point, all of the matching has been done based on sort of this similarity score based on these numeric vectors and so on. So that's all great, and that works reasonably well. But LLMs are very capable, and one of the things they can do really well is actually read documents for you and tell you if that document is useful or not. So after you do your sort of standard RAG and your matching based on similarity, one of the things that has worked very well for us is having the LLM actually review each paper, read the paper, and then tell me if it's relevant or not. Don't just use like a numeric vector to tell me that. And so this is kind of an interesting step where we have an LLM actually review. We give it a set of sort of criteria. Here's what I'm looking for. We develop a set of criteria. Here's what would constitute a good source if it does A, B, C, and D. Read this source and tell me, does this refer to A, B, C, and D? Yes or no? And so we have it go and read through hundreds of papers and rank score each of those papers, and then create sort of a stacked rank of the sources. So for anybody out here building RAG systems, this is a powerful, slightly expensive, but powerful approach to improving performance. Even with all that said, RAG systems have some significant limitations in what they can do. And so I wanted to highlight a couple of examples of cases where this type of an approach falls apart. The first one is summarization questions. So an example of that would be if we go to the chatbot and we say, give me a summary of the latest 10K annual report from Google. All right, because of the way RAG systems are structured, and that they go and they look for sort of matching chunks, and they bring those chunks in and then try to summarize those chunks. If you ask it to do something like this, at best, it's probably only going to grab a few of the chunks out of that annual report, but not the whole thing. And so it's not, without sort of making adjustments to your system to account for something like this, it's not going to do a very good job at answering this type of summarization question. Secondly, comparison questions. So if we have two people, maybe we're hiring for a job and we're looking at two candidates, and we ask a system to go and look at the open source contributions of candidate A and B and give me a comparison of the two. A RAG system that's sort of scanning the internet is also not going to do a particularly good job at this in its sort of most basic form. Why is that? Because it sort of takes this as one query. It goes, it tries to search for kind of maybe contributions of Jack and John in one shot. It doesn't find anything because Jack and John never work together on anything, and so it's not going to give you what you want. The third type of situation where RAG can fall apart is a multi-step analysis. So a question like this, tell me about the risk factors of the highest performing rideshare company in the US. If we as humans were to read this, we would immediately know, okay, first step is, what is the highest performing rideshare company in the US? Is it Uber, Lyft, something else? Probably one of those two. But let's go figure that out first. And then once we figure that out, now let's go and look up the risk factors. So we might go to annual reports or analyst reports or something like that. Okay. So this type of multi-step query is also another area where standard RAG systems tend to fall apart. And then the final one is multi-document synthesis. So if we ask it to given some large corpus of articles, tell me about the pro arguments from article A and the con arguments from article B, and then create a table comparing the pros and the cons from the two articles using our internal style guide to organize that table for us. It's also not going to do a very good job at this, right? By kind of going through this relatively simplistic motion of sort of taking this, converting this to a numeric vector, doing a similarity lookup with all the vectors stored in our vector database, finding the similar chunks, feeding those into a large language model, it's very unlikely that it's going to give you a good answer to this type of a question. Okay, so what can we do to answer these types of questions? This is where the idea of agentic AI comes in and gets interesting. And I'm going to refer to this as what I call agentic AI. So you've probably talked a lot today as well about AI agents. It's obviously a hot topic right now. I wouldn't necessarily refer to these things as sort of Agents, I think some people would, but I think it depends on your definition. There's a lot of definitions there. So let's just call it agentic because it has sort of agentic components to it. This is a standard RAG system, right? So query comes in, we create an embedding of it, we get our vector, we do a lookup in our vector database, find similar embeddings, grab the text from those chunks, feed it into our large language model, pass a response back to our user, right? Some of the limitations here is it's single shot, meaning we just do it one time. It's not iterative, it's not multi-turn. We don't sort of review and go back to the beginning and do it again. We just do it one time and we send out whatever we've come up with. We don't really make much of an attempt to understand the intent of the user's query, right? Again, we're going off semantic matching, so better than just your standard keyword matching, but we're not sort of putting a lot of focus on trying to get at what are they actually looking for. And then number three, we've got some limited flexibility in what data we can actually use to answer this query, right? Because presumably we structured this system in a way that it's hooked up to some external body of knowledge. It's a vector database where we've got a bunch of embeddings of documents stored. Maybe we've hooked it up to like an index of the internet or something like that, and we're doing an internet search. But we've got some sort of limited places where it can go look for information. So now we go from that to what I would call an agentic search, okay? And so we add a few different things in when we talk about an agentic search versus a standard RAG. The first is that it uses reasoning. Maybe it's a reasoning model. Maybe it's using more of your standard LLMs, but sort of prompted in a way to execute sort of step-by-step reasoning. But either way, we typically go through a step-by-step process where we start by trying to understand the intent of the user. What is the user actually trying to get at? And that's step one. We then go through kind of a multi-step process. We do what we call query planning. So given what we think the user is trying to get, how should we structure our querying to find relevant information to answer that question, right? Where should we go look? In what order should we look? If it's a multi-step analysis question, like we just saw in the last slide, maybe we need to decompose that original query into multiple sub-queries and execute each one individually, and then combine the results at the end. So we go through a query planning stage. Then we go through and we execute our search. And during our search, we have the ability to use what is typically called tools. And so basically this just gives the LLM options in terms of where to look for information. And so we're no longer kind of bound to searching only within a single place, maybe a single vector database, but we often give it multiple places to look. So one might be, maybe we have multiple vector databases, maybe we've got, we're going to give it access to the internet, and we're going to use an API to do an internet search. Maybe we're going to connect it to various APIs to pull different types of information. Maybe we're going to allow it to query a SQL database. But we'll give it access to sort of different sets of information located in different places. And based on its planning phase, we'll allow it to decide where it wants to look and in what order it wants to look through those sources. We then typically, well, not typically, sometimes we'll go through kind of then one final stage, which is after it's done its planning, after it's searched for information, after it's used an LLM to generate a response, we'll do a review and critique of that response. We'll go back and see, does our response meet what we think the user's original intent or need was, yes or no? If yes, great, let's return it. If no, let's go back to the beginning and let's redo it. Okay, so real quick, I wanted to show you kind of a real-life case study of this in action. So I mentioned our company Inquisite. One of the tools we provide researchers is what we call our AI Research Assistant. One of the things it does is searches the research literature to answer complex questions with answers supported by cited sources. So this is kind of the typical way that a researcher would go and search for something, use a tool like Google Scholar. They put in similar experience to normal Google. You get your blue links and you've got to kind of scroll, and you're given a few words from each one to try to see which one of these might be the most relevant. And you kind of click and you have to get into the paper and sort of maybe read the abstract. abstract to maybe read the whole paper to figure out sort of what are the most relevant papers. So a system like this optimizes for recall versus precision, meaning that it's trying to surface all of the potentially relevant sources for you. It doesn't want to miss something. So it's going to give you a long laundry list of sources. Many of those are relevant, some of those are not, but it's left to you to then kind of figure out which ones are relevant and which ones are not. This is our system, Inquisit, and so we do a kind of a different search, which I'll explain on the next slide, but this is what we return to the user. We return a set of sources at the bottom. For each of the sources, we use our large language model to generate kind of a quick bullet point highlights for each one, so you can kind of quickly decide, is this worth spending more time on? Is this worth digging into or not? We also return up at the top kind of a synthesis of the most relevant sources. As you can see, that we cite, not only cite the source, but we actually provide the exact sentence or two that the large language model is using to generate all of the statements in the synthesis. So we support the statements in the synthesis backed by actual text from the sources. And then we have our assistant on the side. You can actually ask questions. So if you want to kind of dive in quickly to like ask a question about a specific research study, like what was the population or what was the sample size used in that study, you can just ask and it'll go and it'll read through the paper and it'll get your answer to your question. And so that's one of the things we do. We optimize for both recall and precision. So we try to find all of the relevant sources because we also don't want to miss any. We want to give you all the relevant sources, but we only want to find the most relevant sources. We don't want to give you a laundry list of 100 different papers which you could consider reading. We want to get you like right to the 10, 20, papers that are the most relevant to what you're trying to study. Okay, and so this is how we do it. We follow a lot of the things I mentioned on the previous two slides in terms of our flow. So query comes in, we do a query decomposition. We try to understand what is the researcher actually trying to ask, what information are they actually looking at. We break it down into multiple subqueries if we need to. We then go and we execute. We start with a keyword search. So we formulate not just one keyword search, but we formulate a number of keyword searches using the original query and creating kind of different variants of keyword searches. We collect a large candidate set of normally hundreds of papers, maybe a few hundred papers. We then do a second step of our search process, which is a re-ranking based on a semantic search, and we also include some metadata about the paper. So we prioritize, for example, highly cited papers over less cited papers, et cetera. We then take our kind of pool of top papers, let's say the top 50 or 100. We have an LLM that reviews all the papers. So it goes through and reads at least the abstract, if not the whole paper. And then does some scoring and then ranks based on relevancy. And then we take the most relevant papers and we create that little synthesis that you saw earlier. We're adding in a final step to this process, which is sort of a review and critique. So we have an LLM determine, have we sufficiently answered the user's question or not? If not, we'll go back and we'll iterate again. So very quickly to wrap up here, a few of our learnings from, I guess, 4 months or so now of being in production with this type of a system. One is that agents are sexy, they're interesting, they're powerful, they're hot right now. But you can also go wrong with agents. So you need to think very carefully about sort of the balance of control. Do you want to allow the user to have more input and more control over the process, or do you want to try to kind of guess what the user wants and use an agent to do it? Right? And to be honest, a lot of times the answer is give the user control. When we first started, we were allowing our models to control more of it, like deciding kind of where to look and, should I only search the last couple years of literature or should I search the last 30 years of literature? And now we just have user inputs for it because we decided actually it's better if we allow the researcher to, customize that rather than trying to guess that on their behalf. Secondly, there's definitely, as with all things, a trade-off between cost and latency versus performance. So that process I showed on the last slide. That's fairly extensive. It's not cheap necessarily. We've done as much as we can to optimize for cost, but not cheap, although it works well. And so that's an important thing to think about, is that trade-off between how much money are you willing to spend on an average user's query versus what performance level you want. And then number 3, when you're doing any kind of search, it's an important decision to think about how much focus you want to put on the sources that you're surfacing for the user versus how much focus you want on the synthesis of those sources. So you could see on that slide I showed the Inquisit user interface, we actually put a lot of focus on the sources themselves, the papers themselves, because we want people to see what are the papers, to be able to quickly kind of dig into them, to open them up, read them, versus if you recall back my second slide, I think, where I showed that ChatGPT interface, it's like one little kind of tag with like wikipedia.org or something, right? So clearly, like, their focus is on the synthesis of it, not so much kind of like the sources. And so that's also a very important consideration. I know at least some of you out here are building kind of AI search, and so kind of that distinction between focusing on sources versus synthesis is really important to think about. So that wraps it up. I think we're just about on time. So I'm going to hang out here. I think we have a break now. So if there are any questions, happy to hang out and chat. Otherwise, thank you for listening. Hope that was a lot better than the equations that I showed at the beginning. And look forward to meeting many of you. Thanks.